SDS polyacrylamide gel electrophoresis, or Sds-Page, helps identify the quantity and approximate masses of proteins in a sample. It is a powerful technique used to resolve proteins according to their masses. Because proteins differ in size, shape, and charge, a protein sample is first denatured with the anionic detergent SDS. To a tube containing the protein mixture, a loading buffer is added. This loading buffer contains several components, including sodium dodecyl sulfate, SDS, an anionic detergent containing a negatively charged head group and a hydrophobic tail. The buffer also contains glycerol, which makes the protein solution more dense, such that it sinks to the bottom of a well when loading a gel. A charged dye, such as bromophenol blue, is included and enables the researcher to track the progress of the gel while it is running. A reducing agent, such as dithiothrietol or beta-mercaptoethanol, may be included to disrupt any disulfide bonds present in the sample. When the sample is heated, the SDS molecules bind to the proteins, disrupt their hydrophobic cores, and cause them to unfold. If a protein is composed of several subunits, the SDS not only unfolds the protein, but also dissociates the protein into its individual polypeptide chains. If reducing agent has been added, any covalent disulfide bonds will be broken, further contributing to the unfolding process. The denatured proteins become uniformly coated with negatively charged SDS molecules, so they all have similar shapes and charge-to-mass ratios. The mixture of denatured proteins is then transferred from the tube and loaded into a well that has been cast in the top of a polyacrylamide gel. Typically, a mixture of proteins of known masses is also loaded into one or two of the wells. The resulting ladder of protein bands from these lanes can be compared to the sample of interest to estimate the masses of proteins in the sample. In an electric field generated by a power supply, the negatively charged polypeptides migrate through the gel toward the positive electrode at the bottom of the gel. The migrating polypeptides are slowed by the tangled network of polyacrylamide. Smaller polypeptides travel more easily and quickly through the pores in the network than do larger polypeptides. Because the polypeptides have similar charge-to-mass ratios, their speed, and thus the distances they travel through a gel, are dependent only on mass. Based on this principle, proteins are separated according to their sizes, with low-mass proteins having greater mobility than high-mass proteins. Once migration is complete, the gel is removed from the power supply. The protein bands can be detected by treating the gel with a protein binding dye such as Kumasi blue, then washing away the unbound dye.